Assalamualaikum. My name is Muhammad Nasruddin, metric number 231361727, and we are from Team Misfit, and today we will present our case study on Proton CIM integration in Malaysian automotive assembly for sustainable production. This presentation examines how assembly process and material handling system operate within a computer-integrated manufacturing environment and how this system contribute to efficient and sustainable automotive production. Proton Tanjung Maling plant represent the physical automation of environment of our case study. The facility consists of several manufacturing stages, including engine and transmission machining, stamping, body assembly, paint and trim, and lastly, final assembly. To support this operation, the plant incorporates optimized logistic flow, storage system, and material handling paths. The facility is also designed for scalable and flexible production through modular manufacturing line and digital system such as MES and WMS, making it a suitable example of a modern automotive manufacturing environment. This slide explains the engineering fundamentals that enable automation in Proton manufacturing environment. First, physical motion is generated by actuators such as electric motor, servo drive, and robotic mechanism, which are used to move vehicle bodies, components, and production equipment. To control this movement, sensors are used to detect conditions such as position, presence, speed, or distance. The sensor data is then sent to a controller which processes the information and determines the appropriate action based on predefined control logic. For example, when a vehicle body reaches a workstation, a sensor detects its position and sends a signal to a controller. The controller then stops the conveyor and allows the next assembly operation to begin. Finally, feedback loop ensures that the system operates accurately and reliably. The controller continuously compares the actual system condition with the desired condition and make correction when necessary. This principle of motion this principle of motion control, sensing, control logic, and feedback form the foundation of automated assembly and material handling system used in modern automotive manufacturing. This case study focuses on Proton Tanjung Maling manufacturing facility and its use of CIM integration to support automotive production. The engineering challenge extends beyond simply manufacturing vehicle. Proton must simultaneously improve production efficiency, maintain product quality, optimize material flow, enhance worker safety, and support sustainable manufacturing practice. These objectives often create conflicting requirements such as increasing production speed while maintaining safety and sustainability standards. Because the problem involves multiple constraints, the stakeholder, and possible solutions, it qualifies as a broadly defined engineering problem. The assembly process in Proton manufacturing system follow a structural sequence beginning with body assembly, followed by painting, trim installation, and final assembly. From an automation perspective, the process relies on sequential operation where each stage must be completed before the next stage can begin. The manufacturing workflow is supported by process planning system that translate product design into detailed assembly procedure. In addition, quality control activities are integrated throughout production to ensure consistency and reliability. This automation principle enable efficient, repeatable, and high-volume vehicle manufacturing. The material handling subsystem ensures that components are delivered to the correct production area at the correct time. At Proton Tanjung Maling facility, logistic flow, storage system, and material handling paths support the movement of material throughout the factory. Modern manufacturing facilities increasingly use automated guided vehicle or AGV to automate repetitive transportation tasks. AGV improve productivity, optimize resource allocation, and reduce workplace accidents while supporting Industry 4.0 manufacturing strategies. Together with systems such as WMS and MES, the material handling subsystem enable efficient and scalable production operation. Assembly and material handling system perform different but complementary functions within Proton manufacturing environment. The assembly subsystem is responsible for transforming components into finished vehicle through process such as body assembly, painting, and final assembly. Its primary focus is product creation, quality, and process execution. In contrast, the material handling subsystem focuses on moving and supplying components throughout the factory. It manages storage, logistic flow, and transportation activities to ensure that material arrive at correct workstation when required. Therefore, while assembly systems create value by manufacturing the product, material handling systems create value by maintaining continuous production flow. Both subsystems must operate together to achieve efficient and reliable automotive manufacturing. System efficiency in Proton manufacturing environment depend on the effective integration of assembly and material handling system. Through CIM integration, manufacturing execution system and warehouse management system coordinate production activities, material availabilities, and logistic flow in real time. Several bottlenecks can affect manufacturing performance, including material delivery delays, equipment failures, quality defect, and inventory efficiency. This challenge can be addressed through CIM-enabled technology such as predictive maintenance, automated quality inspection, AI-powered supply chain management, and optimized logistics system. At Proton Tanjung Malim facility, modular production line, logistic infrastructure, and digital management system support scalable production while maintaining operational efficiency. By reducing downtime, minimizing defect, and improve material utilization, CIM integration enhance productivity and support sustainable automotive manufacturing.
Today I'll be presenting on how Proton integrates CIM into its automotive assembly plant for sustainable production. CIM is a system that connects all manufacturing processes from design and planning to purchasing and distribution using computer technology. It links CAD, CAM with production systems, enables data-driven decision and connects platforms like MES, WMS, and ERP. At Proton Tanjung Malim plant, CIM acts as a supervisory backbone across the entire 280-acre facility. It does four key things. It monitors all production stations in real time. It centralizes data from sensors and PLC panels across every zone. It triggers automated alarms before failure cascades, and it supports green manufacturing by tracking energy use and coordinating just-in-time inventory. Moving on to how CIM is structured at Proton, it follows the ISA 95 control hierarchy across four levels. Level 1, over 500 sensors and 300 welding robots collect physical data. Level 2, Siemens S7 PLC control robot cells, conveyors, and safety systems. Level 3 is the supervisory CIM layer. This is where the MES tracks every vehicle body in real time and dispatches the correct program to each station automatically. Level 4, SAP ERP manages and supply chain, while WMS coordinates GIT delivery and carbon emission tracking. The data flow is seamless from body welding capturing weld current and force, paint ovens monitoring temperature, to end of line vision scans determining whether a vehicle is released or sent for rework. Finally, let's look at the real impact CIM has on Proton operation. CIM enables three major improvements. First, multi-model scheduling. The MES dynamically sequences the X50, X70, and Saga on the same production line with zero manual intervention and zero changeovers stoppages. Second is the predictive maintenance. CIM analyzes the vibration and temperature data from all 300 robots, scheduling maintenance proactively, resulting in 50% fewer breakdowns. And third is sustainable operation. CIM auto shuts idle machines and optimize paint oven cycles, cutting energy use by 25% and supporting Malaysia's net zero 2050 goal. And in conclusion, CIM is not just an automation tool, it is Proton's foundation for smarter, greener, and more efficient manufacturing. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is MASTURINA binti MOHAMAD HISAMUDDin. So for this section, I will explain how computer integrated manufacturing or CIM helps Proton balance production efficiency with sustainability and safety requirements. So, one of Proton's main challenges is increasing vehicle production while maintaining workplace safety and reducing environmental impact. So, higher production rates can lead to increased energy consumption, equipment wear, and operational risk. To address this challenge, CIM provides several solutions such as predictive maintenance, automated inspection system, manufacturing execution system or MES, and dynamic scheduling. So these technologies help to improve productivity while reducing waste and downtime. So Overall, CIM enables Proton to achieve a higher production output without compromising sustainability and safety objectives. Okay, next, this slide highlights how CIM contributes to environmental sustainability in Proton's manufacturing operation. Real-time energy monitoring helps reduce unnecessary electricity consumption, while just-in-time inventory management minimizes excess material storage, predictive maintenance extends equipment lifespan, and reduces waste generated from unexpected failures. In addition, automated quality control reduces defective products and scraps materials. By integrating systems such as MES and warehouse management system, Proton can optimize material flow and resource utilization throughout the production process. As a result, CIM helps reduce energy consumption, lower material waste, improve resource efficiency, and decrease the overall environmental impact of manufacturing activities. So next, beside productivity, safety is also a critical aspect of CIM implementation. In automotive assembly plants, several hazards exist, including robotic welding station, conveyor system, electrical equipment, and pen operation. These hazards can cause injuries, electric shocks, or chemical exposure if not properly controlled. CIM incorporates various safety functions such as continuous machine monitoring, automatic fault detection, alarm system, and safety PLC integration with emergency stop system. Examples of safety controls include light curtains, safety interlocked emergency stop buttons, lockout tagout procedures, and proper ventilation system. Therefore, CIM helps Proton create a safer working environment while reducing operational risk and workplace accident. For a CIM system to operate effectively, compliance with regulation and professional standard is essential. In Malaysia, relevant regulations include OSHA 1994, the Environmental Quality Act 1974, and the Factories and Machinery Act 1967. This regulation focuses on worker safety, environmental protection, and equipment certification. At the international level, standards such as ISO 14001, ISO 45001, and ITF 16949 and IEC 62443 provide guidelines for environmental management, occupational safety, quality management, and industrial cyber security. Engineers must also follow BEM and NIEM professional ethics by prioritize public safety, maintenance professional competency, protect confidential information, and promoting sustainable engineering practice. Compliance with these requirements helps Proton maintain safe, reliable, and sustainable manufacturing operation. Okay, so next, this slide discusses future technology that can further enhance CIM implementation. Technologies such as industrial Internet of Things, artificial intelligence, digital twin, collaborative robots, and additive manufacturing are expected to transform automotive manufacturing. For Proton, these technologies can improve predictive maintenance, support electric vehicle production, enhance quality control, and increase manufacturing flexibility. On a global scale, this innovation can reduce carbon emission, strengthen supply chain resilience, improve competitiveness, and accelerate Industry 4.0 adoption. In conclusion, future CIM technologies will continue to improve productivity, sustainability, and competitiveness in the automotive industry while supporting Proton's long-term manufacturing goals.
Wabarakatuh. I'm Syahirah binti Makdawa, bernombor matrik 23136356 dari RY32 Group 1. So in this slide, we will discuss the ethical issues related to the cyber security and the data privacy in Proton CIM environment. So as manufacturing system become more connected through computer, network, and automation technology, they are also exposed to the cyber security risk, which means the unauthorized user may gain access to manufacturing system, cyber attack may disrupt production's operation, and confidential company information could be stolen or misused. Another important issue is the data privacy. Modern CIM system store a large amount of the information, including employee record, production data, and company information. If this data is not properly protected, it may be exposed to unauthorized parties and affect the stakeholder trust. As engineer, we have a professional responsibility to protect confidential information, to ensure the secure of the digital technology, and report the cybersecurity risks when they occur. We must also promote ethical behavior and accountability within the organization. In addition, Cybersecurity requires teamwork, which means engineer, IT specialists, and manager must work together to create a safe and secure manufacturing environment. For Proton, addressing cybersecurity and data privacy issue is important to support secure manufacturing operation, protect stakeholder information, and strengthen trust in Industry 4.0 technology. Next, for BEM, IEM Engineering Ethic. This slide will explain how the ethical principles of the Board of Engineering Malaysia or BEM and the institutions of the Engineering Malaysia or IEM can be applied in Proton CIM environments. So the first principle is a public safety and welfare, which means the engineer must ensure that CIM machines, robot and automated system operate safely to protect worker and the public. Safety should be always the highest priority in the engineering activity. And the second principle is the integrity and honesty. Engineering must provide accurate information, report issue truthfully, and make the decision based on the fact and professional judgment rather than personal interest. Another important principle is confidential and data protection, which means the CIM system handle production data and company information. Engineers should be protect these informations and prevent unauthorized access or data breaches. And also engineers must also maintain professional competence, which means working within their area of expertise and continuously improving their technical knowledge, especially in CIM and Industry 4.0 technology. In addition, engineers should be support sustainability by promoting in energy efficiency and reduce waste and also contributing to environmental responsibility manufacturing practices. And finally, professional conduct and leadership are essential, which means engineers should demonstrate respect, fairness, accountability, and lead by example while promoting ethical behavior within the organization. By following the ethical principle established by BEM and IEM, Proton can maintain safe, reliable, and sustainable manufacturing operations while strengthening their trust in its Industry 4.0 initiatively. Next is about the team leadership and coordination strategy. So based on this slide, it will show about how our group apply leadership, teamwork, and professional ethic throughout this project. So to ensure the project was completely successfully, tasks were divided according to each member's strengths and expertise, which means every member was given a clearly responsibility and contribute to different sections to the project. We maintain effective communication through the regular group discussion, information sharing, and collaborative problem solving. This helps us coordinate our work, solve challenges efficiently, and ensure that all tasks were complete on the time. And also, we almost discuss about our problem in our group WhatsApp. And also for the professional ethic were also important throughout the project, which means we respect each other opinion, maintain accountability for our responsibility, and also support one another whenever difficult arose. And as a future engineer, leadership is not only about leading a team but also about promoting cooperations, responsibility, and ethical decision making. Overall, effective leadership, communication, teamwork enable our group to successfully analyze CIM integrations in Proton automotive manufacturing environment while maintaining professional and ethical working practices. So we are at the end of our discussion. Based on this project, we can conclude that computer integrated manufacturing or CIM plays an important roles in improving Proton automotive manufacturing operations. From our finding, CIM help increase efficiency by integrating assembly and material handling system. It also improve product quality through automations, real-time monitoring, and digital technology. In addition, sustainable manufacturing practices such as energy efficiency and waste reduction support boost environmental business goal. We also found that cybersecurity and data privacy, also ethical leaderships are essential to ensure safe and responsible manufacturing operation. Looking ahead, the future of industrial automation will involve greater use of artificial intelligence, the industrial Internet of Things, and also autonomous system And we also have data-driven decision making. At the same time, future engineering leader must continue to promote innovations, sustainability, and ethical responsibility. Overall, CIM is a key driver for the proton industry for 4.0 transformation in helping improving efficiency, quality, sustainability, and also competitiveness in automotive industry. That's all from us. Thank you.